Hello guys, today we have a first video lecture about Tower of Hanoi problem. So this lecture is not about theoretical stuff, but more about discussing the problems, how to approach problems. For Tower of Hanoi, we're going to discuss how we can approach solving the problems using logical methods. Okay, so, and that includes also mathematical induction, which we'll come to later. So for now, guys, I want to ask you again that you have to first review the lecture first. Okay, lecture slides provide you all the necessary details, and only after that you should come to watch these tutorials. Okay, otherwise it's not going to be very useful for you. And I hope, guys, that I see you, all of you, on my lectures if you are attending my lectures. But if not, then that's okay. Say hi to me if you see me. Okay, so let's start with Tower of Hanoi problem. Now, if you remember that the standard problem is given like this, right? We have three pegs, A, B, C, right? And on one of the pegs, we have a certain amount of disks that we have to transfer them, okay, from one peg to the other peg. And the rule is that you can move only one disk at a time, okay? And you cannot put larger disk on top of the smaller one. So smaller ones must be on top of the larger ones. So those are the rules. You remember them from the lecture, right? Now we have the standard problem, but how do we actually come up with recursive formula? And after that, the closed formula. Okay, so first of all, let's try to play around, right? So the beginning, we're gonna see that actually how we can deduct, okay, the formula for recursive function and for closed form function. So this is based on deduction. But we have also other methods, right, like repertoire and perturbation and many more, which we'll come to later on during this course. Okay, so let's first indicate, okay, that the minimum number of moves needed to transfer n disks, okay, from peg A to peg C, okay, is given by this letter Tn, okay. So remember that we're interested in the minimum number of moves, right? We don't want to transfer the disks, okay, in the maximum amount or on average, but we want to transfer these disks in the minimum possible, okay, number of moves. So over here, let's say actually that we have n disks, right? So this goes on and on. So I'm indicating Tn to be my number of minimum moves, right? We needed to transfer n disks from A to C. Now this is my starting position and C my final position. Now let's try to play the game, right? So if I play the game for n equal to 1, so remember that T1 corresponds to n equal to 1, right? So this is n equal to 1. That means we have only one disk. So if you have one disk, how many moves should you make, right, to move one disk from A to C? Well, obviously only one, right? Now what about if you have two disks, right? So this will be corresponding to T2. Now if you have two disks, right, what you do is, first of all, right, you move the upper one over here, right? And then the bottom one you move over here, right? So you have one move, second move, and then this disk goes on top of it, right? So we have in total 1, 2, 3, 3 moves. Okay, by the same logic, when you have 3 disks, right, T3, how many moves will it take? Well, if you play it, right, you're gonna see that it's gonna take you 7 moves. And when you have 4 disks, if you play it around, okay, if you play it actually, then you will see that you will need at least 15 moves to move okay, 4 disks from peg A to peg C. So that's what we had initially, right? Okay, so this is what I call observations, right? So observations. So remember from the lecture, right? We need observations. So observations are initial data. So based on that initial data, we're gonna make, okay, some guess. But first, before that, we have to see if there is a pattern in our data, right? In our observations. So first of all, I want to try to find recursive formula, right? So recursive formula. Recursive formula. Now you already know the recursive formula, right? But how do we come to that actually? So we're going to use these observations. So I have only 4 observations. So let's say based on these 4 observational data, we will try to, okay, come up with a guess for our recursive formula. Okay, so remember in recursive formula or recursive function, you have to connect, okay, one of the values with the previous value of the function, right? So you have to connect the current value of the function with the previous value. So over here I have 3, which is t2. So if I want to connect it with t1, well, I have to somehow express, okay, 3 in terms of 1, or basically t2 in terms of t1. Okay, so what I see is, I see that actually 3 is, well, 2 plus 1, right? Okay, and I can write it as like this, 2 times 1 plus 1, right? Okay, so maybe I can say that actually this 1 corresponds to this 1, right? But I don't know if it works out actually. So this is the method of deduction, right? We're trying to guess it. Okay, maybe it works out. So let's see with other data. So 7, I want to express it in terms of 3, or maybe basically t3, I want to express in terms of t2. So then I want to say then maybe it looks like 2 times 3, which is 6, and I need 1. So 2 times 3 plus 1 is actually 7, right? So it looks like this 3 and this 3 correspond, right? So we're starting to see some pattern. So maybe let's see if there is a connection between 15 and 7, right? So basically t4, we want to express in terms of t3. So again, I see that actually 15 can be written as 2 times 7 plus 1. Well, actually it looks like there is a pattern, right? So this 3 corresponds to this 7 corresponds to this 7, and this 1 actually corresponds to this 1, right? And if you want to check it, okay, you can come up with a couple more observational data, right? T5, T6, T7, and see that actually the pattern holds, okay? So looks like there is a pattern, okay? So there is a pattern, okay, which is that the current value of t is connected to the previous value in this format. 2 multiplied by the previous value of t plus 1, okay? So I'm going to make a guess, okay? So based on this, we're going to say guess that Tn equal, right? If I'm saying Tn, remember I'm looking for general formula, right? For recursive function. So I'm saying therefore Tn. So if I say Tn, which is my current, then what will be the previous is actually Tn minus 1, right? So 2 times Tn minus 1 plus 1. Okay? So this is my guess. And I'm saying that this is a guess. Why? Because we have not proved it. To make it a formula or function, right, we have to prove it. and we prove it using mathematical induction. But this is going to be an exercise for you guys. We're going to do that in class, okay, if you're in my group. So this will be an exercise. We're going to say right now, we're going to assume that this is proven. And what I want to do, I want to prove the closed form. But before that, I want to also derive the closed form, okay? How we can actually derive it, basing on a similar approach. Okay, so this is how we derived, or basically guessed, recursive function, okay, for Tower of Hanoi problem. Now we want to do the same for closed form function. Now let's see. So closed form function basically says that there is no recursive relation between values of t, which is quite efficient for us, right? So if you have a recursive formula, when n gets very large, it's going to be actually very costly for you to compute the number of minimum moves, okay, in this Tower of Hanoi problem. So therefore, and not only in this problem, but in all recursive problems, we want to come up with a closed form, because the closed form is much more cost efficient, which basically means that it computes for you the values, right, much faster. Okay, so to find or to guess the closed form, again, I need some observational data. So let's say we're going to get our observations. Okay, so observations, I'm going to use the previous. So remember that when n equal to 1, I have t1 equal 1. When n equal to 2, t2 equal 3. And n equal to 3, t3 equal 7. And n equal to 4, t4 equal 15. Now, you already know the closed form, right? But how do I actually come up with it? So the method is actually trying to see if there is any kind of pattern without a recursive function, which basically without calling on the previous value, okay? Okay, so maybe, let's see, right? I can write 3 as, well, 4 minus 1, okay? And sometimes, guys, you have to play around, right? You have to play it and see what works, what doesn't. So it's not going to be always like exactly to the point. Okay, so let's say 7. We could see that maybe 7 I can write as 8 minus 1, right? And 15, yeah, I see that maybe also 16 minus 1. And I see that actually 4, 8, and 16 are kind of like powers of 2, right? Right? So basically, 4 is 2 to the power of 2, right? And 8 is basically 2 to the power of 3. And 16 is 2 to the power of 4, right? And what do I do with this? Well, 1 is actually 2 minus 1, right? And 2 we can leave it as this, yeah, which is basically 2 to the power of 1 minus 1. So it looks like we have a pattern, right? So the pattern is basically we have the power of 2, right? And we have a minus some constant. So in this case, minus 1. So power of 2. As you see that if n changes, right, the power of 2 also changes proportionally. So based on this, right, we're going to guess that closed form for Tower of Hanoi function is going to be 2 to the power of n minus 1. Okay, so this is closed form function. Okay, now again I'm saying this is a guess, well, because we're deriving this based only on 4 observations, right, which is not enough, yeah, to say that this is the actually true function, right, for Tower of Hanoi problem in closed form. We have to show that this works for all the values, right? Or we can use mathematical induction to prove this. So we're going to use mathematical induction to prove that this is the true formula. Okay, so you remember math induction from discrete mathematics, right? We have 3 steps. Step 1, you have base case. Base case, which is basically when n equal to 1, right? And when n equal to 1, I see that if n equal to 1, I have 2 to the power of 1 minus 1, right? Equal to 1. Well, which is true, we can verify it by hand, right? Okay, true by inspection. We can verify it basically playing the game, right? Okay, so this is my base case. Now for the second step, I'm going to say that we assume, right? Assume that when n equal to k, and k is integer greater than 1, right? So greater than 1 and integer. So we're going to assume that when n equal to k, then, okay, this formula, so Tn is going to be now Tk, right? Because we're plugging in instead of n, k. That formula will be again correct. 2 to the power of k minus 1. So we're saying that, assume that when n equal to k, then this is true. What does it mean this is true? Well, basically we're saying that this calculates for us the value accurately, right? So this is what we're assuming. Now in the third step, we're going to prove, okay, for n equal k plus 1, that this formula also works, okay? So prove for n equal k plus 1, Tn equal 2 to the power of n minus 1 is true. So we need to prove this. Okay, so what does it mean n equal to k plus 1? So if n equal to k is my current step, then n equal to k plus 1 is my very next step. So what I'm saying basically, base case, okay, works. Now I'm assuming that if for n equal to k, my function also calculates for me accurately, right, the value, then for the very next value, right, it should also calculate it accurately. So it must be true for that if the formula is correct. Okay, now in this case, to prove this formula, we're going to use this recursive function. Okay, we're going to assume that this is proven, but this is an exercise for you, remember? We're going to assume that this is proven and we're going to use it in our proof. Okay, so I'm going to start with n equal to k plus 1. So Tn equal, if n equal to k plus 1, then this is going to be T of k plus 1. Okay, now remember recursive function. So the recursive function is given by this formula, right? That Tn equal 2 times Tn minus 1 plus 1. So I'm going to use it in this step over here, okay, for this one. So what I get is 2 times Tk plus 1, right, according to the recursive formula. Now what I also know about Tk, about this, well, in the second step, right, we assume that tk is equal to this. Well, that tk also is accurate. So basically tk equal to this value, 2 to the power of k minus 1, is also accurate. So we assume this one. So if we are assuming this, then we can use it in our step, okay, to validate or to disprove it. So I'm going to say 2 times multiplied by, I'm going to plug in instead of tk, 2 to the power of k minus 1. Okay? And I have plus 1 over here. So what I do next is, I simplify this. Open up the brackets, right? So I will have 2 times 2 to the power of k is going to give me 2 to the power of k plus 1 minus 2 plus 1, right? And which is basically 2 to the power of k plus 1 minus 1. This is exactly what we needed, right? We're starting with this, that when n equal to n equal to k plus 1, right, that the tk plus 1 gave us this result, 2 to the power of k plus 1 minus 1, which is actually true, right? Because k plus 1 is our n. So if you plug it in back, you're going to get t to the power t of n equal 2 to the power of n minus 1. So this is actually proven. And this is how you go, okay, to prove the closed form using mathematical induction. Now we're going to have an exercise. I'm going to give you an exercise here. You can try to do this exercise yourself, and when you come to the lecture or to my practice sessions, please show it to me. You might get a bonus point if you do it correctly. So let's say we have the problem slightly changed. Okay, again, same Tower of Hanoi problem. We have the starting position in A, and we have the final position now not in C but in B. So let's say this is my final position, and there is one more restriction. Okay, the restriction is that we cannot move around between A and B. Okay, so no direct moves. So basically, you have again 3 pegs, A, B, C. Your final starting position is A, final position is B, but you cannot move directly from A to B and from B to A. Okay, you can only move through C. So that is from A to C, from C to B, only like this. Okay, so if you have this restriction, what will be the recursive formula? Okay, the question is, so Tower of Hanoi, exercise for you. Find recursive and closed forms and second is prove them using induction. So this is an exercise for you. I hope you to see all in my lectures and in my practice sessions if you are in my groups. But if not, then you're free to come around, okay, and say hi and show me the problem if you got it correctly. Or you can show it to your instructor as well. But this is an exercise for you. Again, we have 3 pegs. Okay, now no direct moves between A and C. Starting position A and final position is B. So you have to move all of these disks from A to B. So if you have this restriction, then what will be the recursive formula? And obviously, it will be different, right? And what will be the closed formula? So this is the problem for you. I hope this is a useful problem for you, okay, to get started with, okay? So guys, if you like this lecture, if you like this video, please like and subscribe. Just kidding. Guys, if you have any questions, you are free to write to me in Teams or to come by in my office hours or in my lecture classes and ask your questions there. Thank you all and see you guys.